everyone. Thank you for coming. And you're like so many. That's very nice. Actually, I'm really happy to see that the graduate students thing are actually more popular than others in that. It seems like that it also is very encouraging in trying to convince and motivate other graduate students to give seminar because frankly, you people are interested in what they are doing. So thank you very much for coming. There are probably other donuts, I hope, or available. You get the one that you want, or some where are the drinks? Yeah, in the Trader Joe's bag if you want the drinks. Yeah, that's and today we're excited to have Swanson going to give a seminar today, so that will last roughly 40 minutes. Do you mind if we'll ask quick question during the presentation?
Yeah, that's fine. You can interrupt me or wait till the end.
Okay, and so we have some time at the end to ask more like in-depth question. Well, thank you for coming, and the floor is yours. So we'll give you a 10 minutes notice for 45 minutes.
Okay. Sounds good. Hi, everyone. I'm Diana Swanson. I am part of the ESRG group here, led by Jim Clemens. Today, I will be talking about the Endurance sounding rocket mission. So the New Hampshire team led the density and the neutral density and composition measurement as part of this mission. Glenn Collinson was the PI and Alex Gloser was the science team lead from Goddard. And there are many other people involved as well. This is just a few of them after launch from the Arctic. But so these are NASA, NASROC scientists, all sorts of people involved. So today, first, I will talk about the science goals of this mission and introduce the ambipolar electric field. Then I will talk about the instrumentation and some of the techniques used to make the necessary measurements. I'll focus on the neutrals and then give you a brief story of the launch, how it went, and show you some preliminary results from the neutral density. So the Endurance mission, the main objective was to measure the ambipolar electric field of Earth for the first time. This electric field is a driver of the polar wind that leads to ionospheric outflow. And so this increases the scale height of atomic oxygen and allows ions to flow out of our atmosphere. So essentially this is set up as electrons are gyrating following the magnetic field lines. Ions are too, but they feel the force of gravity because they're heavier. And so we get this small separation in charge. This separation creates an electric field called the ambipolar electric field. And this actually retards the electrons, but accelerates the ions out along the open field lines. And understanding the measurement, how large this electric field actually is, can help us understand the ions that are flowing out, which species are able to flow out, and can help address questions like the habitability of Earth's atmosphere, why we maintain it. Spoiler, this is a very small value, so we won't lose our atmosphere anytime soon. Be orders of billions of years through this loss mechanism. So not only do we want to measure the value of this potential, but we also want to understand how it's distributed as a function of altitude. So one of the main driving processes of this is incident EUV solar flux acts on the atmosphere. It creates photoelectrons and secondary electron populations, and it also leads to heating of the thermosphere. So these dynamics of the neutrals affect the distribution of this potential as we go up in vertical height. And so the neutral measurements are important here and will be used as inputs into the polar wind outflow model, which will help us understand the underlying physics of this distribution of potential we will measure. So a little bit of theory, we can start with the generalized Ohm's law and include some terms like an electron pressure gradient, this first term in red, and DDS is integrating along magnetic field lines. And then we have an electron inertial term and then a collisional term. If we make the assumption that the mass of electrons is small, we can simplify that to this bottom value here, which is basically dependent on the gradient of the pressure of electrons. that there's been arguments that that's an okay assumption. But then we went to Venus and we predicted the value of Venus's ambipolar electric field to be about 0.9 volts based on taking the gradient of the pressure term. And then we went and directly measured the ambipolar electric field, so basically the left-hand side of this equation, and found that it's around 10 volts. So this discrepancy tells us that these assumptions aren't quite right. We have to include some more of these terms, including the neutrals, and that'll be part of this measurement at Earth. Is we'll directly measure the left-hand side and try to understand the physics on the right-hand side and what we need to include in this measurement. So at Earth, the predicted potential is about 0.4. There's been an upper limit set, about 2 volts. And you can see that depending on what this potential actually is, it changes. So this y-axis is the percent of ions escaping. And so if it's low potential, not much atomic oxygen is escaping. If the potential is higher, a lot more is escaping, and we could, hardly keep any protons if it's very high. So these dynamics of what this value actually is dictating the ions that are staying in that ionosphere, which is important for understanding the ionosphere, but it's also important for what ions are flowing out into the magnetosphere and filling those populations in the magnetosphere and leading to all of those dynamics we like to study as well. So how will we directly measure this electric field? As we said, EUV solar radiation is incident on our atmosphere. That is energizing photoelectrons that are excited, and they're flowing out along the open field lines. We know based on atmospheric physics and general atomic physics what this spectra should look like. So that's what this plot is here. This is observation from the Atmospheric Explorer E mission. This is the spectra of photoelectrons we expect to see. And if this spectra is shifted by some amount, that shift in EV is the measurement of our electric field. Because as I said, that electric field is retarding the electrons that are trying to flow out. The peaks here are pretty close together. And so that makes this a little bit more challenging because we need a high resolution instrument to be able to measure the spectra and the peaks in it. So previously this technology hasn't existed, which is one of the main reasons we haven't made this measurement on Earth before. Now that technology exists, and so it's by combining an electrostatic analyzer and a retarding potential analyzer together. So basically a top hat ESA is a very common instrument on many space flights, including rockets and satellites. And it has this 2-hemisphere geometry with a gap to allow electrons to flow through, and a potential is applied. And on this inner hemisphere, that potential is stepped for the Endurance rocket from 10 eV to 1 keV. And that will give basically an energy spectra like plot B here. But you can see it has a wide resolution, and we can't get that resolution too small without getting rid of too much signal. So we're always kind of weighing this signal to resolution problem in experimental science. And so one way they can get this signal from the ESA, but then they can also stack a retarding potential analyzer underneath, which has a much higher resolution. And so a retarding potential analyzer is basically acting like a filter. So it's like a grid with an applied voltage, and if the electrons have enough energy, they'll make it past that filter, and if they don't, they'll be rejected out. And so this plot here, the black line shows counts, and so if you have, as you go up in voltage, you're letting all of the electrons through, and then at some point they fall off, and you're using your filter, and you're no longer letting electrons through. And if you take the slope of that line, that's this blue curve, the differential counts, and that's giving us our kind of effective spectra here, which is a much higher resolution measurement. it's difficult here to then span a large energy range, and so we can have the ESA on top to filter out and keep our signal higher, and then scan through with the RPA. So the combined technique looks more like this bottom plot here, and then there's a channel electron multiplier at the bottom with a high gain to actually measure these electrons once they make it through the entire instrument. So that kind of theory is what makes up the photoelectron spectrometer. And the photoelectron spectrometer is made up of 8 DSAs, dual electrostatic analyzers. We can just keep adding acronyms. But the dual electrostatic analyzer looks like this. We think it's dual because there's 2 on here, 2 per arm here on endurance. So this is the endurance payload, and there's actually 8. So there's 4 booms that you can see here, and they fold out once in space, and there's 8 DSA. And basically they found after flying this on the Dynamo 2 mission, they weren't getting enough signal, so they just stacked more of these. They flew 1 then, they just stacked 8 of them together here to get enough signal. But you can see, so the ESA on top, the top hat has a resolution of about 16%, and then with the RPA under that, it'll get down to about 0.5%. And this will take about 10 seconds per scan. So as we're flying, I'll show you the rocket trajectory later and stuff. So as we're flying up, we'll get about 240 measurements through the exo base. So if we use a polar wind outflow model, we can make a prediction of what our measurements will look like. So this black curve here is the expected spectra of Earth's atmosphere, and the black line is with the 0 potential. So if there wasn't an ambipolar electric field, we expect that spectra, and then the blue line is with an electric field of about 0.4 volts. And so we'll be able to use the polar wind outflow model to compare to the actual measurements and understand the shift in the spectra we measure versus the expected well-known spectra. This middle plot here shows simulated data from the PES instrument, and you can see the resolution is somewhat a function of voltage here, but the resolution is generally less than 0.2 EV, so we should be able to measure this 0.4 EV drop. And then this is kind of how we're going to do it in space, or how we did it in space. And so the peak of the photoelectron production is around 150, basically below 200 kilometers. And we'll turn on and start taking measurements around 200 kilometers and fly up to an apogee. It ended up being about 768 kilometers, and we'll be making measurements with the DSA all the way up. And so you can see here that the expected potential drop is about 0.4 volts, but we're also interested in the spectra as we climb up and the distribution of that. And so the neutral measurements, as I'll talk about later, we're expected to make those from about 200 to 500 kilometers here, and that'll be an input into the polar wind outflow model. So the payload, this was kind of fun. It was 47.001, meaning it's the first of its type. So the first stacking of the NICA motor, Oriole, and carrier, and then the payload was up top here, and this is what it looks like folded out in space. So there's this sweeping Langmuir probe on top, and that allows us to make electron density measurements, and also understand the spacecraft charging, which is really important if we need to know the potential of the spacecraft if we're trying to measure the potential. We have the axial ionization gauge on top and 1 radial on the side for neutral density measurements. We have the NMS off the side for neutral composition. So these were all provided by our team at UNH. And then the kind of main hero of our rocket, the photoelectron spectrometer, is off the side here, and some electric field booms. The trajectory, we launched from Nelson, Svalbard, Norway, 78 degrees north, off this little island here. We reached apogee about 768 kilometers, and then splashed down in the Greenland Sea. Basically, the flight went like so. We launched, deployed our nose cone, turned everything on, started taking measurements around 200 kilometers, made it up to apogee, again, a little bit under our expected 800. And then we started falling down, and we actually pitched over and turned the rocket over. This allows our IGs and neutral measurements to still be in mostly rand direction. And we continue to make measurements as we fall down, or downwave. And I'll talk about later, but it's important to note that this was through the polar cap and along the magnetic field line. So the neutral measurements, these are important. We were able to make density and composition measurements. They help us understand the photoelectron generation. So where that's happening, how the ions are produced and transported, and then where collisions are taking place with the neutral. So the photoelectron neutral collisions, and how the transport of electrons are impacted by those collisions. So up here we have the ionization gauge for neutral densities, and then here's the MSIST run. MSIST is an empirical atmospheric model, and it includes inputs from the current state of the ionosphere. So that includes things like KP, so the general index of geomagnetic activity, and F10.7, measuring the EUV input. And that gave us this expected spectra from the model. But it's important for us to make these in situ measurements that are co-local with our electric field or electrostatic analyzer measurements, so that we have co-local coincident measurements to go as we make this precise measurement through the exophase. One thing to notice here in these densities, there's a large range of densities, about 6 orders of magnitude as we fly from 100 to 800 kilometers. And so this is a difficult measurement to make, to be able to span this high of a range. And we're able to do that with our ionization gauge. And so this is a standard Bayard Alpert gauge. You can find these on basically any vacuum chamber here in Morse or anywhere else. We use this off-the-shelf part from Anelva and modify it. And it works by applying a current to these filaments here in red. And those filaments are yttria-coated iridium. And when a current's applied, they boil off electrons. And those electrons create ions as they collide with the neutrals. And the proportion of that is important. And so those ions are then accelerated by this internal grid. There's a potential applied to this, so the ions are accelerated towards the middle of the sensor and then collected by the ion collector wire down the middle. So the neutral pressure is proportional to this ratio of the collected current and the emission current we applied to this filament. And it's proportional by the sensitivity constant. I'll talk about how we can calibrate and solve for that. So we put this gauge on the side of this accommodation chamber, and then we call this whole thing an ionization gauge as well, so a little bit confusing. But the inside of this instrument is a perfect sphere, and this is in its open state here, so we call this the door. It's open, gas is allowed to flow through these screens, and neutral gas into this accommodation chamber. The gas diffusively refracts off of the internal surface, and it importantly accommodates to the same temperature as the instrument, and then is measured by the ionization gauge. So now we know the temperature and the pressure of the neutral gas inside our instrument. Like I said, we have a large dynamic range to cover, and we can do that with this instrument. We get about 21 bits at 1 kilohertz rate measurement. We use custom electronics boards to control this, including controlling the emission current of the filament, and that's a feedback loop because it's somewhat proportional to the temperature. So we keep that, for this mission, we kept that constant at about 400 microlens. And see if this plays. So this is what it does in space. It opens up. This is extremely sensitive to density as we've seen. And we're flying on rockets, which are generally short flights. So we don't want to measure the gas we brought from our lab. We want to measure space. So we do that by vacuuming these out basically in the lab. So, and then we open them in space like this, so that we don't spend a lot of time outgassing. We're able to measure space. That adds a lot more engineering challenges and headaches, and we have to deal with O-rings and gaskets and doors opening and things like that. But that allows us to make the measurements in space. And then we calibrate these instruments. So here's some quick calibration data. Maybe hard to see the labels here, but this was stepping the voltage. So I basically used a known resistor as the filament instead of using the IG, and applied a voltage to that. With Ohm's law, we can then predict an expected current from that. And that's the current that our boards should also be giving. And so if I stepped the voltage, we got out this current here from our analog to digital converter. And then we have to turn that into some physical units and calibrate that. So here are the values for the offset and the gain to convert from bits to microamps. And I think that's a pretty good fit. You can see the red line barely, it's plotted, that's the expected, and the blue line is the data we measured for this band. So we can apply those current calibrations, and then we can also do some pressure calibrations and solve for this sensitivity constant here. We did that by putting the gauges on the vacuum chamber, and then in this case, inputting some nitrogen. And we slowly increase the pressure, so you can see the steps. It was every couple of 2 minutes or so. So it takes about 3 hours to do this calibration in the lab. And here we're using the ANELVA as kind of the ground truth. This ANELVA gauge was on the side of our vacuum chamber. And then so was the axial and radial ionization gauges that we flew. So these sensors were all there together, should be making the same measurement. And you can see the sensitivity values varied a little bit. This is multiple pressure runs together, and I averaged them together to get a sensitivity factor of about 1/7.05. And if I applied that to this plot, and you see they overlap pretty well. So there's maybe some more work to do there, but this is for rough the first calibration. This is looking pretty good as well. So then the journey begins. We built our instruments, calibrated them, ready to go to the Arctic. Here's Lance with our big crates. Pushing them through Logan Airport. Our first hiccup, we were overweight. So we spent half an hour on the ground at Logan Airport, moving our space instruments around, power supplies around, stuffing cables into our backpacks. Made weight. Then we got on our flight, flew to Norway. Our bags did not. Then they didn't get on the flight the next day. Then they went to Salt Lake City. Finally made it to Amsterdam, where they ended up on a pile of luggage because they were baggage workers on strike. So all this to be said, we ended up flying up to Longyearbyen with our equipment. We spent a night on the MS Farm, this beautiful boat. We got off the boat because our instruments weren't with us, and stayed in Longyearbyen while the boat went further north to Ny-Ålesund. After about a week living in the Arctic and taking stat med tests and all sorts of things, we finally got our equipment. Lance went up before me a couple of days, and by like day 5 or 7, I'm not even sure, I finally flew further north to Ny-Ålesund.
Wait, you used research funds to go on that fancy cruise?
Yeah. But we didn't go on the cruise, we took the flight, which I kind of think is better anyways, because these are some of the coolest views we'll probably ever see. This was a little plane, like 4,000 feet above the Arctic. And we landed in Yellowstone, this small research town, the northernmost settlement in the world. There were COVID outbreaks, there were all sorts of issues, but we finally got ready to launch and we started thinking about what were our launch conditions. We have about 2 weeks. What are our go, no-go conditions for science? And so one of them is that we need to be along open field lines. The ambipolar field is most important here. This is where the ions are actually leaving our atmosphere and ionosphere and into the magnetosphere. This is where the pressure gradients are steepest. So we want to launch along open field lines. There are some interesting dynamics here with electron precipitation, things like that. So we used the ISCAP radar, so this team was online with us, helping us determine where the open closed field line boundary was, and we made sure we were within the open field lines to launch. Second was daytime. I didn't have good pictures, so here's a reindeer. We want to launch in daytime because we need photoelectrons to be present. That's what our main measurement is. And we want minimal geomagnetic activity. Basically, we want nominal conditions for this measurement. We don't want aurora or field line currents. The thermosphere is known to heat up and expand when there's geomagnetic activity. That would broaden our photo peaks. We don't want that. We want low EUV solar minimum type conditions. And so we were on the clock to get this launched in 2021 before the sun starts acting up. And in this particular window, the first 3 days looked pretty good in terms of low activity in the last 3 days, but the middle didn't. So we were a little bit pressed to try to launch early. And this is what it looked like on the first day. So we reported out like midnight or something. Didn't really matter what time it was, the sun never set. So I took a nap and I woke up and it's like complete whiteout conditions outside. So we know we're gonna have a couple days before the sun starts acting up more, but we didn't launch on day 1. We did eventually launch on day 3. And I muted this because we're all counting down and screaming and going crazy. And it was fun in this launch too to see the first stage fall down, because we went so high vertically, it fell down really close to where we were. So here's the payload in the final condition launch, and then here's one of the first pieces of data we got to see. So this is from a 12 megapixel camera at apogee looking back at the Earth. So this, I'm not sure what's clouds and what's now. This is looking back at the pole of the Earth. So what did the IG data look? As I said, we take basically the ratio of collected current and emission current. So this middle plot here is the emission current, right around 400 microamps, and we're measuring neutral gas, and so we're very sensitive to neutral gas. So you can see that somewhat in these spikes here, and that's due to the ACS, or the attitude control system. And so that's neutral gas that they're using to help point the rocket. So we see that we need to be pointed right. That's just part of our measurement. And you can see when it pitches over, we get even more noise here. We measured a good collected current as well. We take the ratio with our calibrations and get this top plot, which is the IG pressure. We also measured the gauge temperature. As I said, that's important for making our measurement. And you can see when it pitches over here too. So we have pressures, and if we start digging into what this looks like, the blue curve here is from that top plot on the last slide, the gauge pressure, but it's much higher here than we expect to see. So this means that we probably had some outgassing. We have some screens on the top of the instrument to filter out ions and things. maybe those PC boards were outgassing. We used some getters to keep the pressure low. Maybe we seem to have some sort of source here we don't understand well, but we were able to fit a background. Basically, we weren't, like I said, our measurement range was only about 500 to 200 as we fall down. And so we basically say way up at apogee, that's supposed to be orders of magnitude lower density. So we'll call that a background. That's due, basically most of our measurement here is due to some gas source we don't fully understand. So we'll fit to that and extend it down later in flight time. And then we'll subtract that background off of our downleg measurement. And that gives us this corrected pressure curve, the black curve, and MSIS model predicted the red dash curve. So now we think that our measurement's actually looking okay here. I've have multiple IGs, we're launching them every year. And so I have other ones in the lab here I'm trying to test and try to understand if we can recreate this high background to get a better sense of what that is. That's in progress. So we have a pressure, we have a temperature. By ideal gas law, we have a density. So we have a density inside the gauge and we have a temperature inside the gauge. But we know we're flying on a rocket, we're going super fast. That's going to add an extra signal. And that's not actually a measurement of the atmosphere yet. So we can do some kinetic theory of gas and make some assumptions and convert that measurement in the gauge to an ambient measurement. This assumes that the mean free path is greater than the gauge dimensions. Basically, we're at low pressure. The molecules follow Maxwellian distribution, and that the gas accommodates to the temperature of the chamber quickly. And that's the whole point of the accommodation chambers. So assuming the flux into the chamber is proportional to the flux out, and accounting for the ramp and
How do I do that?
So we're assuming flux into the instrument through that aperture is equal to flux out, and we're accounting for the velocity of the rocket by basically using this fancy term that includes S, which is the velocity of the rocket. With this cosine is rocket trajectory versus aperture of the IG normal of that aperture over the thermal velocity. And this gives us a ambient density and temperature measurement. And the results look like this. So here are the density plots. The IG is the black plot and MSIS is red. So the model seemed to do a decent job here. You can see these wiggles here are due to the ACS. Again, I'm just really sensitive to that as we go up. So this is from the axial IG, this is at the top of the rocket. And then we can also calculate a temperature using a hypsometric approach. So this is assuming a stratified atmosphere. And we can, using a seed temperature from MSIS at the top, we can integrate downwards, basically integrate both sides and continue solving for density and temperature. And we iterate over that a couple of times to converge on a density and a temperature result. And those shouldn't be a big factor based on the MSIS seed temperature. There's a little bit more work to do here. Here you can see the wiggles from the ACS, and the distribution in temperature isn't quite as expected. So I'll continue to look at this. The radial IG is a slightly different story. I don't fully understand this. You can see many more fluctuations here. This is actually smooth data to about 1 second. And we see these fluctuations we don't fully understand. This gauge was partially blocked just based on the way it was on the payload, and we knew that going in. It's also much closer to the ACS. We know we're very sensitive to that. And we also have this higher background as we did with the axial gauge. So there's more work to do here to understand this measurement.
That's a quick question.
Yeah,
Did the background vary at all with spin or coning or anything? Was it just?
it seemed to be mostly constant. Yeah,
We're 3x's.
yeah, we're stable.
Oh, okay.
And then I'll briefly talk about the composition measurements. Lance Davis took the lead on this. So we have the neutral mass spec. It's designed to measure major atmospheric species. And the cool thing about this instrument, it has a rotating electric field that impulses perpendicular to the ion beam. I'll explain this in a minute, to create a form of a time of flight measurement for mass spec. And so it's cost effective, it's quick, we don't have to wait to scan over multiple masses, and we have a range of about 0 to 80 AMU. So the neutral particles flow into this accommodation chamber, again, using similar techniques. The ion gauge, we use an ion gauge to ionize the particles. So now we have ions that flow through these optics. There's a incident perpendicular impulse electric field. This electric field is actually rotating, and so we know the speed of that rotation, and then the ions are directed towards the annular MCP at the back. And so we can kind of unravel this measurement of position on the MCP and timing of the electric field to make a mass measurement. Calibration data looked okay, a bit messy, but here we can see a clear peak in helium, oxygen, argon. There's continued work to understand a lot of this noise as well. And then we have the flight data here. You can see a band at about 18 AMU that seems pretty strong here. We saw that also in calibration and actually subtracted that out from this plot here. But Lance was able to do some measurements in the lab and see that material we were using in this front ionizer piece called Altem, a type of plastic, seems to have a similar mass and composition, and same with some of these heavier plastics we see. So we actually have an exact copy of the NMS we launched in the lab, and we have our RGA and lab equipment here, so we hope to make better sense of this measurement as well. So in summary, these neutral measurements will go into the polar wind outflow model and produce a high resolution simulation of the electric field, ambipolar electric field. And then we also, with the DSA, we're able to make direct measurements of the ambipolar electric field. I'm not presenting those results, that's for the PI to do, and we hope to kind of wrap up and hear more about this mission soon from them. And it's been about a year now since we launched, and data processing is going well, but not done yet. Any questions?
Did you do a dry nitrogen purge on your mass spectrometer? Because mass of 18, the obvious thing to think of is that's water outgassing.
Yeah, as much as we could, we had dry nitrogen on our NMS in the lab and then also at NASA. So we can't get rid of all water, but we definitely were purging.
Maybe I could add a little bit there. If you've looked at the mass scale that Diana presented, there's some uncertainty in that scale. That if I look at it, I don't see it at 18, I see it at 16. And so it's, it's a little bit unclear, and it's pretty broad here. So there's really significant work to do here to understand this. And this is mostly Lance's work, as Diana mentioned. He's working on the lab just to try to get that out.
Left is the calibration data.
Yeah, this is calibration data. And then this is white spectra.
And when just on the other, like for your O2, why are there all those other peaks of? Why is it so weird?
So for the left plot, we have subtracted out the background spectrum, the average spectrum that we measured across all our calibrations. So the little funny bits near water, or the same kind of peaks we saw during flight, but the reason it's not dominating that spectrum is because we subtracted it out.
Right, and it looks like you got a CO2 peak in there as well.
You mean the argon peak?
In all three of those spectra, I see a mass peak at around 44, which would be CO2. Yeah.
And what I'm saying is that
Yeah.
we don't have a good zero order, physics-based scale there. We have to go, because it depends on the trajectory of those things through, how long those take. And so we have some calculated and so on that we've done, and they turned out to be a little bit not the same as the data too, so there's some different things, and, we have some insulators in there, and there's a lot of things that need to be understood. And, so don't, the bottom line here is, I'm sorry to jump in, is that mass scale on the bottom is, there should be error bars on that thing, so.
So, forgive me for my ignorance here, because I do not use space physics. And the only people who don't use space physics.
What I drink here.
Are you lost? I saw talk 301 a lot. So you mentioned that you started measuring at 200 kilometers above the Earth's surface. Why was that? Is this like the minimum boundary where you expect to see this ambipolar electric field, or?
Yeah, so you can see the peak of photoelectrons, way back, it is right around 200 kilometers. So the potential drop is happening above that. We also have, limited dynamic range, and so we want to optimize that. We're also going up very fast on this mission, so it takes time to turn things on and get the nose cone off. So that all kind of converged on around 200 kilometers.
How much time does it take to reach 200 kilometers?
I don't have that off the top of my head right now.
To reach where?
200 kilometers.
It's about, I think it's around 100 seconds.
Yeah, a minute and a half.
But you can't eject your nose cone in the lower atmosphere, right? You have to be in a place where you're already in space before you can do your deployment. So
Yeah.
very common with pipes.
So you mentioned you were trying to follow field lines. Is the somewhat dipolar-y field line shape close enough to your parabolic suborbital trajectory that you are kind of following the field line, or do you have to do some correction to make those match up?
Yeah, that would be more on the DISA side work. And I'm not sure exactly how they correct for that. The idea is to mostly fly along, so they don't have to, but of course we weren't exact.
Sure.
I would think that that's one of the things the ACS does, is that I don't think the trajectory has to be exactly along the field line, but it has to be pointed along the
Right,
field.
that makes sense.
So you have data about the density and the temperature. How is that gonna be used to map the electric field?
So that will go into this polar wind outflow model. It's actually one of the inputs to their physics model. When I showed the generalized Ohm's law, you can see some neutral terms in there to account for collision. But the main measurement of this potential drop is just due to the spectra shift from the DISA instruments. So we're supporting in this mission, the neutrals were mainly a supporting measurement.
What did you do with the rocket? Because you said splashdown, just let it sink, or you just leave it?
Yeah, unfortunately, most of these rockets just end up in the bottom of the ocean. And we make the things again and launch them again. So
Yeah, perhaps, probably another simpler question. So you had this voltage measurement for Venus. So I guess my question is, why did we have that measurement for Venus before we had it for Earth? So I mean, maybe you don't know the answer to that question, I have no idea, but yeah. Yeah, the impact of data on the IR.
So my understanding is this type of instrument was on, I don't remember the Venus mission. I know like Maven went to Mars and made a similar measurement. So it's partly just like,
Venus Express,
yeah, Venus Express.
that comes to Venus? Maybe I'm not sure,
I'm not sure, maybe it was that mission, a Venus mission. And for Earth, it's not gonna be a satellite, we wanna go on a rocket, through, and there's a lot of other things to study too, so. This kind of came up as the technology did and the mission opportunity. Great, thank you.
Let's check our speakers. Thank you everyone for coming. So this was our last seminar for this school of years. So I hope to see you with, I hope to see that many people next September, sorry, going to starting again as seminar series. Thank you very much.